So now I would like to go a little bit more deep in this term, which is called direct map cache. In another sense, how we can map the cache to the main memory. What is the scheme or the configuration style that will be used to basically address or connect or relate all of my data that is in the cache in terms of addresses to the address inside my main memory. So direct map, each memory block is mapped to exactly one block in the cache. Lots of memory blocks, of course, must share the same cache block. Why? Because I know now in advance that my main memory is actually larger than my cache memory. And since it is larger, I know in advance that, of course, some of the data that is inside the main memory will share exactly the same location inside my cache. Going back to the example that we have mentioned earlier in terms of the compound and the number of students and the parking lot, I know in advance right now that the number of students actually that are basically living in that compound are a lot higher than the number of parking spots or parking free spots available. For instance, if I have like 200 apartments, and in each apartment I have 5 students as an example. So as a total, I will have 1,000 students living in this particular compound. If I have only 200 spots available, the question is how I can map these 200 spots to these basically 1,000 students. There might be a strategy that you need to take as a manager for that compound in order to allocate that particular parking spots to each student. You need to think of a way that it will be common for all the students to know as soon as they have their numbers in hand, they should know where to park. So the designers actually came up with an idea or with a mathematical formula that can be used for each student to allocate exactly the parking spot number. In another sense, I will distribute for each student as soon as they will join my compound a number. And according to that number, they will understand or they will know after applying that number to this formula where exactly they should park. And they will know in advance that, by the way, you are not the only one that is parking in that spot. There are also other students who are sharing the same spot with you. What you need to do is just plug that number to this formula, and then you will know your spot number. And go and try to park there. If there is any availability on that parking spots, you can park your car. If there is like any other one that is there, then as an example, you have to come and tell us, and then we'll send him or her a warning for 2 hours that he or she needs to move the vehicle or the car in just 2 hours, as an example. You need to put like a certain particular rule, correct? Here is exactly the same. We have the main memory, large number of students. We have the parking spots available, of course, less number. And I know in advance that in this case, many memory locations in the main memory will share the same exact location in my cache. Or in another sense, many students who are basically living in my compound will share exactly the same spot, correct? But the question is how I can formalize that things in a way that will not have any problems between the students. In another sense, I just need to give them a certain particular formula again to use it in order to know their spot location. So for instance, if this is the student number 00001, which is now decimal-wise, it is 1. I would like to know in which parking spots available in that particular place that students need to park. Or in another way, this memory location, I need to know where should be mapped in my cache memory. What I need to do is just like plug this number to this formula, memory block address, which is your number as a student, in this case is 1, modulo the number of blocks in the cache, which in this case is 8, or in the parking example is basically 200. So how many spots are available? In this case, in the cache is basically 8 spots available. In the parking lots, I have 200. Assuming that I'm dealing with this cache, so 1 modulo 8 is what? Meaning 1 divided by 8, what is the remainder? 0. 1, 2, 3, 4, what is the number? 1. So 1 modulo 8 is basically 1, so I will know that I should park in number 1. So this means that my parking spots is this guy. How about this number? This number is 01001. What is that number? 9. So instead of 1, I need to plug here 9. 9 modulo 8 is what? 1. So this means that that guy also will park in the spot number 1. How about that guy? 10001. What is that number? 17 modulo 8. Again 1. So that guy will park in the same spots. If you do this, you will find that this is also need to park in slot number 1. How about this guy? Let's take this example. 10100. What is that? 5. 5 modulo 8 is 5. So this means that I will park to number 101, which is 5. If you do this, you will find that is also modulo is 5. If you do this, you will find the same. So you'll find that all of these are sharing. And if you do this for all of these spots, you will find that there are actually students who are sharing exactly the same spots according to that particular formula. Or in another sense, I have now main memory location that are basically sharing the same exactly one location. So you can think of this as many to one. Many memory location to just one location inside my memory. They are sharing that particular location. If you look also closely, you will find that the spots that are sharing the same location have exactly the same first 3 bits. In this case, it is 001, 001, 00, also 1. And by the way, this is 001 is also equal to the same spot that they are sharing. So student number 1, student number 9, student number 17, all of these, the first 3 digits that they have is 1. And this is also is exactly the same as the parking spot that they have. It is parking spot number 1. The same happened with these other students and so on and so forth. Okay, so now we understand that as soon as you have the first 3 digits similar, you are living in the same apartment, or in another sense, you are sharing the same exactly spot. Correct? The question afterwards, why the first 3? Why not the first 4? Why not the first 2? Why we found in this example that the first 3 need to be always exactly the same? Why the first 3 bits here are the same? The answer to that question, because actually you have only 8 slots. And in order to add this 8 slots, you have 3 bits. And because of that, log 8 is 3. That's why always, since they are sharing the same 001 spot as an example, so they should have all the same exactly 3 digits numbers in their code or in their number, correct? That's why the first 3 bits in all of the shared location need to be the same. So what will happen if this is 16 spots? How many bits do you expect that they will be the same? 4, because log 16 to the base 2 is equal to 4. And since all of them are sharing the same spot, so of course the first 4 digits will be always the same in all of these shared locations. Meaning that all students that are sharing the same spot, they will always have the first 4 digits equal. If they are 32, 5 bits, and so on and so forth. Okay? But then the next question is how I can differentiate between one and the other. In another sense, let's say that my CPU here would like to access address number 1. And since it would like to access address number 1, it knows in advance that I need to go to that slot. When I went to that slot, I found that there is a memory data written here. But how I can guarantee that this memory belongs to 1, not 9, not 17, not this? How I can guarantee that? There should be another thing that we need to think as a management team in that compound to differentiate between a student and another student. Even if they are sharing the same apartment and sharing the same parking spot. So I went there, I read the first 3 numbers, so I understand that they are belonging to, as an example, apartment number 1. But which student? I need to know exactly the student number. So this means that I will need a little bit more bits or more data to differentiate between each student that basically belong to the same or that basically sharing the same parking spot, correct? This data here, if you look closely at these numbers, you will find that this is the following 2 bits. The following 2 bits, the following 2 bits, the following 2 bits. In this case, since this is 32 and this is 8, so you will find with this 32, I need 5 bits. The first 3 bits are similar, so the next 2 bits will be basically used as to differentiate between one memory and another memory location that are sharing basically the same spot, or to differentiate between different students that they are basically sharing the same spot and the same apartment. And these 2 bits, in this case, I will call it the tag. And with this tag, I will know that this is you, not the others. So from 001, I will understand, as an example, that you live in apartment number 1, for instance. But I don't know which one is you. And since you are like 5 sharing the apartment, yes, so I still don't know if this are you or any student from the other 4 or from the rest. But by this second 2 numbers, these tag numbers, I will understand that this is only you. I can now differentiate between you and any other students who are sharing the same spots or sharing the same apartment. And this is what we call a tag. Is that enough? So this is enough in terms of identification, but this is not enough in terms of identifying that the apartment is already ready to be lived in, or the apartment is already filled in with the students, correct? I still need another things to guarantee that there is actually a students who already lived in the apartment. Let's say, for instance, that I have an apartment number 1 that is basically not ready for living yet, under construction. And since it is under construction, of course, the parking spot that belongs to that particular apartment is not belong to anyone, correct? In another sense, I can say that it is not valid. Or if I will find any car there, I know in advance that this not belong to any apartment, correct? Or any students that, or should be like that, shouldn't belong to any apartments or students who live there because it's not valid yet. So this means that I will have another bit that will basically give me a more information in terms of the validity, if this data is valid or not. So first, I will know the apartment number. Second, I will know you, the student who lives in that apartment. Third, I will know that it is even valid or not. Okay, maybe there is an apartment but actually there is no one living there. So even if I went to that parking spot to find a car, I found a car, but this car actually is not valid or it does not belong to any students. So I can easily just remove it. Correct? But it's still addition 1 bit. And that's why here we say like have a tag associated with each block that contains the address information. The block number of blocks always is a power of 2, and we use the lower address bits to assign the addresses. Here, as we mentioned, a validity bit, which will be, as an example, 1 if it is present, 0 if it is not present. Initially, of course, all the data are not valid. So for instance, like in your system, you just restart. So if you just restart, what do you expect you will have in these memory locations? Most of the memory location actually will be not valid. It will be rubbish. There might be something, but it's not valid. I cannot depend on this particular data to begin to work with. That's why from the very beginning will be like validity will be 0. So for this one, as an example, the CPU went to find a particular, as an example, this location. Unfortunately, the CPU did not find the required data. So the CPU will go and bring this data from the main memory and just like copy it to the cache memory and begin to deal with it. And this is what the here trying to show before the reference and then after the reference. If you would like to go to whatever like we have explained earlier one more time here with this data, so I have like many of these locations, and accordingly I should be able to assign each location to a certain particular memory slot in my cache. As we earlier mentioned that we have to do the number that belongs to you as a student, modulo the number of blocks available in your cache or the number of slots available in your cache. If you are doing this number to this guy, you will find that the modulo will be 0, 0, 1. If you are trying like also different places, you will find exactly the same sharing 0, 0, 1. Why 0, 0, 1? Because basically log 8 to the power 2 is 3. And that's why always the first 3 bits will be the same. If you look at this, you'll find also 101, 101, 101, 101. They are sharing the exact same 3 bits, which belong to 101 as we have seen here. Let's go over this example. Assuming that this is basically my cache. So this is my cache. And assuming that I have a memory reference that is like that, 1, 0, 1, 1, 1. And I would like to see if this is available in the cache or not. This is my cache. I have that this is data, that this data is available here. At index 1, 1, 1, 1, I have my validity bit as yes, it is valid. I have the tag as 1, 0, and this is my memory location. So if you look at these first 3 bits, 1, 1, 1, so I know that it should be in this particular location, 1, 1, 1. Correct? Because actually, if you do this modulo 8, you will find that it's basically this one. Or in another sense, you just look at the first 3 bits. If they are equal, so then this means that this is my parking spot. But is that enough? Is this enough to know that this is exactly the data that I need? The answer is no. Because this guy has a 1, 0 is the tag. I need to check if this tag is basically the same or not. Luckily, in this time, I found that this is exactly the same. the 1 0 is equal to the 1 0. So this is basically the correct data. This is just belong to whatever I explained earlier when I mentioned that the CPU needs the data number 1. But for instance, the data that was there was number 9. So when I went to the same location, because 1 and 9 are sharing the same location, I found that there is a data there. But how I can guarantee that this data that I found is basically data number 1, not 9? That's why I have to check the tag. Or in another sense, you know that your friend parking spot is number 1. You know that in advance. And when you went to that parking spot, you found that there is a car there. But how you can guarantee that this car is belonging to your friend, not any other one who is basically sharing the same parking spot? How you would know that? That's why you need the tag number. The tag number, if you know his tag number, you will, or her tag number, you will be able to know that this is in particular that his or her car. So by looking at the tag, I found that this is equal to that. So it's basically no problem about this. So, and then I basically hit. Why I hit? I hit means that I found it. I found means I hit. If I didn't find means I miss. I miss it. What will happen if I miss something? If the CPU needs a certain particular data from the cache, and for instance, I miss this data, what do you think I need to do? Back to the example that we mentioned for the company, and the manager asked the employee that, please, I would like these components. The first thing the employee will do is what? Trying to go to the room, yes, which is in the same floor. If he or she did not find it in that room, what do you think will be the action? Just go to the basement. Go to the basement and grab it from there. This exactly will be the same. If the CPU did not find something in the cache, we'll go to the memory and then we'll copy it to the cache and then we'll begin to interface with it. This is exactly the same concept as we have for the company and the room and the basement. Next, we have another data, 1 0 0 0 0. If I look at the first 3 bits, I know now that should belong to the address 0 0 0. If I look at the tag 1 0, the tag here is 0 1. Oh, this is basically not the data that I'm looking for. Even if it is sharing the same exactly parking spot, but it's not the same. And since it is not the same, so I miss. And if I miss, what I need to do? Just to go to the main memory, bring the data, copy it to my cache. So if I miss, I have to fetch it from the memory, and now I have overwrite whatever I have here with the new tag to this particular tag, and the data is valid. So what will be the case if I would like 11101? I went again to the first 3 bits since they are the same. I went to 101, but unfortunately, the valid bit here is no. So this means that I miss. If I miss, what I should do? Again, go to the main memory and bring it and overwrite and make it valid. And as I mentioned, we might face a problem like that from I'm just restarting. From the very beginning, I'm assuming that all of the data or most of the data are not valid. But this does not mean that I can't use that spot. So I will go there, it is not valid, I will grab the correct data from the main memory and just like copy it to the cache. And then I begin to interface with this particular data. So with this cache example, so this is exactly the same as we just went through the animation book. So I don't want to go over this again. But now assume that we have this problem and we would like to solve it. Consider a cache with 64 blocks and a block size of 16 bytes. And then my question is, to what block number does address 1200 map to? So now I have 64 blocks. So now I have 64 blocks from 0 all the way to 63. Yes, I just redraw the 8 that we had earlier horizontally. I just like flipped them vertically and increase the number to 64. So this is what I did. Okay? But in addition, in each of these blocks, I have actually 16 bytes. 1, 2, 3, all the way till 16. So from 0 to 15. And since I need to address each byte, so actually I need to think about how we can do that. And then my question is, to what block number does address 1200 map? In another sense, if you as a student has a number of 1200, which block or which floor you are belonging to, or which apartment, or which whatever you will call it, you belong to? So we can solve this actually by 2 different ways. First, I can say like, okay, so let's see. Basically, if I divide the 1200 by 16 and just floor it, what is that number will give me? Which will basically give me 75. And then after I know that this is 75, what is exactly, or where is exactly number 75 belong to my 64 mapping cache? This actually will give you 11. In another sense, you have a very big memory that has like a blocks. And each block here you have 16 bytes. Correct? So you have apartments. Each apartment, as an example, you have 16 rooms. Okay? Or 16 students. And I'm distributing the numbers to these students. After distribute the numbers for these students, for instance, you find that you are 1200. And I'm trying to ask you, so where do you think you should park? First, you need to know to which apartments do you need to be belonging. Correct? So if you look at this is number 0, 1, 2, 3, all the way 16, 17, 18, 19, 20, blah, blah, blah. You are basically 1200. If you do this, you will find that actually you are in block number 75 here. So if you are in block 75 here, which block number you should use in your cache? Since your cache is not big as your memory, it has only 64 out of these. That's why you need to do 75 modulo 64. And you will know from that calculation that is actually equal to 11. So you belong to spot number 11. Is that clear? So this is one way of thinking about solving that problem. But actually, there is also another way to solve that problem. Assuming that I have here 32 bits, and I'm using these 32 bits to give an address. To give an address to what? To give an address for each byte that is actually in my cache memory. I have 64 blocks. In each block, I have 16 room or 16 bytes. And I have to define an addressing scheme that can address each byte in my whole cache. In another sense, by looking at a certain number that we will design right now, you will understand that you are targeting byte number 2 in block number 3, for instance. Or byte number 6 in block number 63. Or whatever you would like. Okay? How we can think about that? Again, here is my blocks. I have from 0 all the way to 63. So I have 64 different blocks. In each of these, I have 16 ones. So I have from 0 to 15. How many bits do I need to address just one block? Or in another sense, how many bits do I need in order to differentiate between different 16 bytes? Or 16 different rooms. I would like to give them an address. How many bytes do I need? There are 16 different locations. I'm trying to ask you, you have 16 different locations. How many bytes do you need to address these 16 different locations? Four. You need 4 bytes. Because 2 to the power of 4 is 16. Since I have here 16 different locations or 16 different rooms, you basically need 4 bits to address that. And this is what I call it here. From 0, the first 4 bits, I will use it to address this guy. Next, I need some bits to address which floor or which block number. Since they are 64 different places, how many bits do I need to use in order to correctly address any floor or block number? 6 bits, because 2 to the power of 6 is 64. So by using this and by using this, I can address actually any bytes here. I can tell you from these 6 bits that it is in 64 blocks. I can tell you from this guy that it is the first byte as an example. Correct? So by having this scheme, I can actually address any byte in my cache. The rest will be the tag. Anything here, the rest will be the tag to differentiate between students who are sharing the same exact spots in my cache. Because this will be the parking spots available. So I can have a garage that is actually 64 floors. And in each floor, I have 16 spots or 16 free spots for cars. But I know in advance that all of these spots will be shared by a lot of students, correct? So I found a car there, so I can address the car location. So I know there, I know exactly the address location, but I don't know to which student it does basically belong. And from the offset, I will understand, from the tag, I will understand that this is basically belong to a certain particular student. Okay, so we did understand what you already mentioned, but how this will help us in getting the same number that you just showed us in terms of 75 and 11. Okay, so look at this 1200. Write 1200 in bits. I am telling you that the first 4 bits is showing you the byte, is showing you the byte number. So if you look at this, you will find that it is 0000. So this means that I am targeting byte number 0. But which floor or which block I still need to see. It is byte number 0. Okay, so how I can know which floor? I told you the following 6 bits. Okay, so 1, 2, 3, 4, 5, 6. So this is the following 6 bits. The following 6 bits, which number is giving you? What is that number? 11. That number is 11. So I'm telling you that you are actually in block number 11, byte number 0. But this also gives you another important information. That in block number 11, I have from byte 0 all the way to byte 15, correct? So this means that if byte number 0 is 1200, so 1200, 1201, 1202, all the way till 1215 are basically in the same block number, correct? correct? And that's why I wrote here that this block maps all addresses between 1200 and 1215. We have already proved it. Correct? Not only that, if you look at this number, forget about all of these things, just like this number, and you would like to know which block inside my main memory. If you read this number, you'll find that this is 75. Yes, but this is actually, it's not my interest. My interest is to know exactly where is the location of my parking spot. If I'm interested to know which apartment number, I need to know the 75. But if I'm interested to know where exactly I should park in my garage, I need the information that is actually in floor number 11. And it is spot number 0. And from this scheme, we have been able to do that. Also, another thing I would like to highlight before moving forward, that the structure hazard problem that we had earlier with main memory, we can face also with cache memory. Just to remind you, with the structure hazard problem meaning that I face a structure problem. Structure problem meaning that two different classes are sharing exactly the same spot on the same exactly time. So I would like to access the data memory and I would like to access the instruction memory exactly the same time while they are in the same place. And because of that, we have decided, if you remember, to split the instruction memory from the data memory. And here is exactly what I would do. I will face the same problem that I would like to access the data memory in the same clock cycle that I would like to access the instruction memory. And because of that, just to split this from that, then I shouldn't get any problem. So now consider this example that I have the main memory word reference like that. 0, 1, 2, 3, 4, 3, 4, 15, meaning the CPU at the very beginning would like to access data that is basically address 0 in the memory, address 1 in the memory, address 2 in the memory, address 3 in the memory, and so on and so forth. And we would like to know where is exactly these addresses, their locations inside my cache. In another sense, we would like to know that number that belong to students, where is exactly they need to park, which parking spot they have. And assume also that I have only 4 parking spots, only 4 parking slots available. If I have only 4 parking slots available, how many bits do I need to address my cache? So I have 2 bits. So if I have 2 bits and I have 4 slots available, 1, 2, 3, 4, just think about that the same example that we took earlier, that I have the 8 slots distributed horizontally, I will just like flip it like that. So instead of 8, I will have them 4, squeeze them to 4. Okay? So I have this guy is address 0, 0, this guy is address 0, 1, this guy is address 1, 0, this guy is address 1, 1. Also in this part, I will add the tag that is corresponding to each student. So I can differentiate between each student and the other while I am allocating the stuff. The first beginning, all of my cache is basically empty, so there's nothing there. And the memory would like to access address 0. Where is address 0 should be located? Again, we need the management office give us a formula. It's too easy. Just plug my number to that formula. I will be able to know where I should park. Your number is 0. 0 modulo 4 is what? 0. So your parking spot need to be in number 0. When you go to number 0, the CPU went to number 0, it didn't find anything, so it missed. If it missed, so this means that the CPU needs to bring all of the stuff from the main memory. Correct? So I went to the main memory and then brought the memory 0 location. Correct? And assume that I would like to write all of my numbers in 4 bits. The first n numbers will belong to the spot location, the next m numbers will belong to the tag. I'm asking you, what do you think should be the n and what should be the m? And I'm telling you that I will write all of these numbers in 4. Oh, you just told us earlier in our example that in the first 3 bits should be always the same, and this is belong to the address number, and all of the rest will belong to the tag. And how did you decide that the first 3 should be the same? Because we have 8 blocks. Log 8 to the power to the base 2 is equal to 3. Here we have 4 spots. Correct? 4 spots. So log 4, the base of 2 is equal to 2. Correct? And that's why the first 2 will belong to the address or to the sharing basically spot. So anything that will have the first 2 as 0, 0 will share the same spot. Anything that they will begin with 0, 1 will share the same spot, 1, 0, and 1, 1. The next 2 thing or the rest will be for the tag. If I would like to write 0, 0, how I can write 0, 0? It will be, how I can write 0? It will be 0, 0, 0, 0. So the first 2 zeros will belong to the spot. The next 2 zeros will belong to the tag. It's exactly the same things in that example when we have the first 3 numbers, which was 3, 0, 0, 1, belong to the address, and the rest belong to the tag. In that example, in that other example, the first 3 bits belong to the address, the next 2 bits belong to the tag. Here, I have the first 2 bits belong to the address, the following 2 bits belongs to the tag. How about the 1? I will go to know exactly where I should park my car. 1 modulo 4 is what? 1. So this means that I will go to number 1. I did not find, so I miss. And this is memory 1. I will go to grab it. Of course, memory 0 was already inside my cache with this tag. In another sense, actually all of these 4 blocks that I'm drawing each time, it's basically the same cache. I'm just taking a snapshot in different time instance. Okay, so I'm just basically whatever I had from the previous stuff will be in the next step, and so on and so forth. So if this is the case, memory of 1, what is the tag of memory of 1? How I can write 1? 0, 0, 0, 1, correct? So the first 2 will belong to this, the next 2 will belong to the tag. Yes? How about the next step? Again, memory 0, memory 1. Here is 0, 0, here is 0, 0. I would like to go to 2. I found that it is empty, so I miss. So I will go to grab it and then copy memory of 2 here, and then again tag 0. What will happen next? Memory 0, memory 1, memory 2, 0, 0, 0, 0, 0, 0. Now I have 3. 3 modulo 4 is what? 3. If this is the case, I will go to 3. Why I'll go to 3? Because actually 1, 1. If I would like to write 3, 3 is like that. Since it is 1, 1, it has to be here in another sense. So I will go, unfortunately, I miss, and I will go to bring memory 3, and again my tag is 0, 0. Next, I have the 4. Let me write all of this again. Here I have memory 0. Here I have memory 1. Here I have memory 2. Here I have memory 3. All of this is like that. I need now 4. 4 modulo 4 is what? 0. I will go to 0. Unfortunately, I did not find memory of 4. I found memory of 0. And since I found memory of 0, so I miss. what I need to do is what? Go and bring memory of 4 and overwrite whatever I have here. So this is basically memory of 4. And the tag will change from 0, 0 to what? Again, how I can write 4? If I would like to write 4, is basically 0, 0, 0, 1, 0, 0, correct? 0, 0 belong to this spot because they are sharing the same first two numbers. Then the next two numbers is basically 0, 1. So my tag is 0, 1. So even if you are living in the same apartment or you are sharing the same spot, but you are a different student, and I need to know that from your tag. I need to know that you are a different student. So also the CPU will understand that this is not the data that is needed, or maybe the data that is needed. Next, I will copy here everything that I had earlier. Memory 4, memory 1, memory 2, and then memory 3. This is 0, 1, 0, 0, 0, 0, 0, 0. And I need 3. I will go there to 3. Did I find 3? Yes, so I hit. I don't need to do anything. I just hit. I found it. It is there. Next, I will copy whatever I had from earlier step. Memory of 4, memory of 1, memory of 2, memory of 3. I will go to this guy 4. How I can write 4? Again, 0, 1, 0, 0. So I have to go to 0, 0. I found that 0, 0, I have the memory of 4. So I hit, correct? And all of my tags are basically the same, did not change from the previous step. Then I will copy again everything. Memory 4, 1, 2, and then 3, 0, 1, 0, 0, 0, 0, 0, 0. But I would like now to go 15. 15 modulo 4 is what? 15 modulo 4 is 3. So I will go to 3. Because if you would like to write 15, it is like that. Correct? The first 2 bits is basically 1, 1 as here. So this is actually I miss. I will remove this or overwrite it by memory of 15. But also I will change my tag to what? To the new tag, because now a new student, Spark, to 1, 1. So here, just like one more time, if I will ask like about miss memory 0, and then the next one, I will miss memory of 1, I will copy it, and then next I will miss memory of 2, I will copy it, and so on and so forth, as we have already explained. If I go to 4, I miss it, and then overwrite with the new tag. It is all whatever I have explained, but I just went over it myself step by step to assure that you do understand that. If you count the number of requests and the number of misses, you will find that this is 1, 2, 3, 4, 5, 6, 7, 8 requests. And unfortunately, I have only 2 hits, and the rest, I have 6 misses. Okay? So with this scheme, we have actually these numbers. So now we would like to go further to understand how we can allocate the numbers correctly in terms of the address design. In another sense, if I have my cache like this, and in this cache, I have all of these locations, how I can design my address scheme to basically address any data that is inside that cache. Before I am trying to do that, I would like first to explain another example from the real life. Assuming that you are the manager of a hotel, and in this hotel, you have, for instance, 11 floors, or let's say 12 floors. You have 12 floors. And you would like to design your room numbers, 12 floors, your room numbers, to reflect very easily your room location. So you and your team came up with a very, very simple idea that, as an example, you just went and see like how many rooms do you have per floor. You find that in each floor, you have actually 99 rooms. Okay? And then, and you cannot exceed that. The maximum is 99. So you just consult with your colleagues, and you came up with the idea that the first 2 digits in any numbers will basically the room number. And anything for the rest will be the floor number. In another sense, if you are giving the number 925 to your guest, you and your guest will understand that he or she is living in room number 25 in floor number 9. If you are giving another one, basically 1125, so this means that they are living in room 25, but in floor number 11. And so on and so forth. And of course, there is no sense that you will actually opposite that, or you will flip that you will use the first 2 digits for floor and then the next 2 digits for room number. No one will do that. You usually go from the smaller to the bigger, and so on and so forth, in terms of the location place. Okay? By the same exact sense, and by the same exact way, we need to think about addressing the location in our cache. For instance, in this example, I have 1024 locations or floors. Or in another sense, I have 1024 floors in my hotel or in my cache. And in each of the floor, I have actually 32 bits. But I don't have to address each bit. I can address only the bytes. Yes? 32 divided by 8 is 4 bytes, correct? So actually in each floor, I have 4 different rooms that need to be addressed. Again, I have 10,024 floors, and in each floor, I have 4 rooms. And I need to build my address scheme in the same way that the other management of the hotel did. Okay, so we need to think exactly the same. I will use the first couple of bits for the room, and then the rest will be for the floor. And then whatever is left, we'll do it for the tag, because in our case, we need even the tag. In addition, we need the tag. So with this, if I have 4 different locations or 4 different rooms, how many bits do I need to address these rooms? 2, correct? So that's why the first 2 bits here in my address will be used to address which room inside that floor. Since I have 10,024 floors, how many bits do I need to address this 10,024? Log 10,024 to the base of 2, you will get that 10. So this means that the following 10 bits will be used to address your floor number or your block number. Anything the rest will be the tag, and the tag will differentiate, as I mentioned you, between all of the others that's sharing exactly the same location. So by this, I can say that you live in byte number 0, block number 0. Here, you will have the 0, and here also you will have the 0. If all of these are zeros, I will know that your room location is basically byte or room 0 in floor 0. If I would like this, so this will be room 0 in floor number 1023. So this means that this will be 0, 0, of course, 0, 0, and this guy will be 1023 in bits. You have to translate that to binary. Is this clear? Why here I mentioned that I have only 4 rooms? Because I mentioned that here in one block, I have only 1 word. And we know in advance that I have to address each byte because it is byte addressable. If it is byte addressable, So this means that I have to address each byte inside my cache. And if I have to address each byte inside my cache, and since I have 32 bits, meaning 4 bytes, so I have to address each byte of these. And because of that, I need actually 2 bits to address these 4 bytes. If, for instance, in the quiz, I'm telling you that, no, your system now is word addressing. It's not byte address. It's not byte addressable. It's word addressable. How do you think this will affect your design here? I'm telling you that it is word addressable. It's not byte addressable. It's word addressable. In another sense, you have 10,000. You have 1,024 floors, but in each floor you have only one room. That's exactly the same thing, correct? If you have only one room, so how many bits? There is no bit. Because if I'm telling you that you are living in floor number 9, you have only one room. You don't have any option. Correct? So there is no need actually for this at all. You will have just 10 bits, and then the rest will be for the tag. So the tag actually will be 22 in that sense. Correct? Did you get the idea? I can play with all of these. The most important things that you understand. The concept. Let's take another example. So here is another example. I am giving you this information. 4 words per block. Cache size is 1K words. Please design this. That's it. So the total size is 1K word. And you have 4 words per block, correct? But you have 1K words. So how many blocks do you need? 1K divided by 4. If you do that, it will give you 256 location, yes? Because 1K actually is not 1,000. 1K, if you remember from the first or second lecture in the review, is 1,024. Correct? So by giving you this, you can actually do whatever I will explain right now. First, the 1K divided by 4, so you know now that you have 256 floors, but in each floor, you have 4 words. So in this floor, as an example, you have word number 1, word number 2, word number 3, word number 4. Okay? And I'm telling you right now, we would like to have the same concept of the addressing scheme that we already explained earlier, but we need to apply that to this example. So again, you have 4 different words. Each word is how many bytes? 1, 2, 3, 4, correct? So you can think is just going from the lower to the higher. First, how I can address each byte here. How I can address each byte here. How many bits do I need? 2 bits. So the first 2 bits here, I will use them for byte offset. Then I have here 1, 2, 3, 4 words. How many bits do I need to tell you that you are in word number 2, not in word number 3, or 4, or 0? How many bits? Again, 2 bits. So the next following 2 bits will be basically to show you which word inside that block. Then the next following bits, how many bits do I need to tell you the floor number? Log 256 to the base of 2 will give you 8. So it will be 2, and then 2, and then 8, and then the rest will be for the tag. If we try to apply these same things in the hotel example, you can think that way. That hotel, instead, it's like very, very big hotel. So instead of having just one building, they actually have 4 buildings. And you can think that, as an example, that building is called north, the other is south, the other one is east, the other one is west. So if I'm giving you 925 is not enough. I have to tell you 925 north, or 925 east, or 925 west, and so on and so forth. Correct? So I have to add more information to you in order to know the location. So I might say 9N25 or 10N25. You'll understand that you are in room 25, you are in the north building, and you are in floor number 10. This will be very easy to go there, correct? Here is exactly the same. I am telling you by just using the first 2 bits that you are in room number 0. And I'm telling you with the next 2 bits that you are in the north, not in the south, not in the east, not in the west. And I'm telling you with the rest, or with the following 8 bits, that you are actually in floor number 10, as an example. And then the rest will be for the tag. And I'm telling you what is exactly the tag. The tag is for everyone can actually share that location. For all other numbers that share the same location, or for all other numbers that they have the first 8 plus 4, 12 bits the same. Is that clear? So now we did understand that I can use the first 2 bits to address which byte basically I have here. I can have the next 2 bits to address which word of these. But also I can think about this a little bit differently. That I can say like, okay, so this word is 4 bytes. I have another 4 bytes, 4 bytes, 4 bytes, or in another sense, 4 multiplied by 4. So I have 16 different locations. Correct? How many bits do I need with these 16 different locations to allocate them? 4 bits. So this means that I will just take these 4 bits to allocate the bytes. The main idea right now is how I can allocate a byte. Because this is the address, the small addressing scheme that I need to address. And then the rest will be the 8 as we mentioned earlier, and the rest will be the tag as we already mentioned earlier. So meaning with the first 4 bytes, you are just addressing where is exactly your byte inside that floor or inside that block. So the problem that we are trying to solve is basically an addressing problem. Where is exactly my data is located? And after I found the location from the tag, I know that anyone who are sharing basically all of the data except the tag can park in the same location. And this is what we exactly explained earlier.